Hello, everyone, and welcome to my presentation. My name is Abdullah Jirjis. I am Researcher Officer at the National Research Council Canada Automotive Service and Transportation Department at the Connected and Autonomous Vehicle team. So let me take you today through this presentation, and thank you for attending my presentation. My presentation is in the Integrated Multimodal System for Real-Time Driver Fatigue Detection and Cognitive Load Assessment. I will take you in a short tour about who we are and what we are doing in general. A quick and brief. We are the CAV lab team that we are located in southern London, Ontario. So mainly we are focusing on perception and mapping for on and off-road environments. So you can see that on the top three pictures, we have a fleet of vehicles with the ICE, hybrid, and electric. So we have all the range of energy type of vehicles that we are able to study each and every and compare them individually. You can see like in the most left picture where my colleague Daniel Chima, he is holding the sensor cube that we place it on top of our vehicles. So you can see here like we have like a three stereo cameras looking for left, right, thermal camera facing forward, and there is underneath it here GNSS IMU internal measurement unit, as well as with Velodyne 128 LiDAR on top. We can simply plug and play, remove, and install whatever equipment we want in order to do our study and research. From inside the vehicle, there is a camera looking down on the steering wheel at the Charuko marker to study the angle and to monitor the angle of the steering wheel, as well as there is a camera looking at the driver. This camera placed in the middle of the windshield for calibration purposes, and then it will be moved to any other corner to not disturb or distract the driver during his sessions. So this is another picture from our lab where you can see that our sensor cube placed on the top of the vehicle, and we take the vehicle on road and do what we have to do. At the back of the vehicle, as you can see, we have a powerful computer where we can have our where all the data have been collected and all the sessions run through. So these computers are powered by Jackery batteries, and that's all about our labs. So let's go to the main topic of today's presentation. So driver fatigue detection really matters because in 2022, we have a 1,768 motor vehicle fatalities and 8,185 serious injuries that have been occurred and collected. Approximately 20% of that number, from those numbers, fatal for collisions that collected from the fatal collisions that involved in driver fatigue. 29.1 of driver fatalities were not wearing seatbelt, and 2.8 that have been reported for fatigue drivers. 23% have been reported for impaired drivers. So those statistics are like highly critical and needed for effective driver fatigue detection system to enhance road and safety in Canada. So our objective for this research to develop a robust multimodal system integrating behavioral, physiological, and vehicle dynamics data to provide real-time early fatigue and cognitive overload detection. The value perception from this is to improve safety for safer driving experience for drivers by minimizing the fatigue-related risks and enhancing the performance by having a real-time monitoring for cognitive load to optimize driver performance under stress. So, a general overview of the system architect in terms of hardware that's being used. So we had used, and we're going to talk about it in detail soon. So the heart rate sensor, which is an armband that placed on the driver's arm, and the facial camera that it's being used is the RealSense Intel camera, and the IMU that have been used is the XSense G 710. Two vehicles that have been used for this research is the Ioniq and the Hyundai Civic. So let's talk about the system. So the system is mainly focused on three models. That's why we call it multimodal. So the first model is driver behavior measurement, where we monitor what is the driver doing, and the vehicle dynamic measurement, where we look at what the vehicle is doing, and the physiological measurement to see what's inside the driver is going on. So those three models will gather and feed and will sync the data using ROS, Robotic Operating System 2, and it feed the CNN LSTM model and divide the result into two classifications or two classes, fatigue and non-fatigue driver. So we move to the first measurement, which is the driver behavior measurement. So the real-time, the first measurement is a real-time driver state monitoring that where we measure the driver fatigue based on eye aspect ratio, mouth aspect ratio, pupil circularity, mouth over eye aspect ratio. This 468 points that are being placed on the driver's face by utilizing the Google Media Pipe deep learning model, and it gives us those four parameters. As well as we can get from that is the driver gaze detection. And here where we can see like the eye and the mouth points that have been placed on the driver's face and driver's eyes, driver mouth, as well as we can see in the last two GIFs where the real-time actual accuracy of the driver's eyes tracking. Moving to the driver physiological measurement, we had used in that stage the heart rate of the driver. Recently, we had added more physiological sensors to this research study. We added the EEG as well and the EMG as well to monitor the driver brain signals and to monitor the driver fatigue signals from the EEG as well as the EMG to monitor the muscle fatigue of the driver. The third measurement is the vehicle dynamics measurement. We use the XSense G710, and those are the readings that we get from the XSense, which is acceleration, deceleration, roll, pitch, and yaw. This is how our vehicle look like, or the data look like when our vehicle is on the road with 128 angle view or field of view of the RGB images and the thermal image that is facing forward, our LiDAR. This LiDAR here that was the Velodyne 32 channel, not the 128. The 128 look way better and way nicer. And the camera from inside looking at the driver steering wheel, and as well as the driver facial measurement using the RealSense camera that is looking at the driver's face. So Fusion framework, multimodal sensor data. So overview, we had used the CNN LSTM model, adapting from existing literature. So the CNN, which is the convolutional neural network, extracting the features from driver behavior, matrices, and just like what I mentioned before, is the eye aspect ratio, mouth aspect ratio, pupil circularity, mouth over eye aspect ratio, and the long short-term memory, which is known by LSTM, analyze the temporal sequences from multimodal data to identify the patterns in fatigue and cognitive load. So the integration, we combine the behavioral and the physiological, as well as the vehicle data for robust real-time fatigue detection. So the experimental setup and data collection, the sensors that have been used, I mentioned all of that earlier, the RealSense camera, the XSense, and the ANT heart rate monitor band. The vehicles that have been hired for this experiment was the Honda Civic 22, and the Hyundai Ioniq electric vehicle. We integrated all these systems using our vehicle computer, running them on ROS operating system 2 in environment of real time data collection, and the data collection was being occurred in urban, rural, highway roads near London, Ontario. And the driver session that we conducted was conducted in a varied lightning condition early in the morning and late in the afternoon. The driver behavior was single driver that had been hired to do the data collection for this proof of concept research to and with no external stimulants like caffeine for the past 12 hours or alcohol for the past 24 hours for better accuracy and safer driving sessions. The driver sessions were being conducted with a full manual control, means no ADAS features was allowed for the driver to use them. And the sessions that was used, the number of sessions was 10 sessions, and each session was between 30 to 60 minutes per session. So the result and performance. So the model accuracy matrices, the precision, recall, and F1 score, as shown in this slide. The precision was 87.3, low false alarms for non-fatigue cases. The recall was 93.2, where a high capture rate of true fatigue cases that reducing the false negatives. 90.1 the F1 score, so the balance metrics for overall performance. The fatigue detection threshold, we had set a threshold manually for this study, but in the future, this is going to be automated based on the driver profile. So for the driver that have been hired for this experiment, the eye aspect ratio was set to 0.2, where below that will indicate fatigue. If the and the mouth aspect ratio was set to 0.8, below above that will indicate yawning, and the pupil circularity was set between 6.5, 0.65, I'm sorry, and above 0.85 to indicate cognitive overload or reduced alertness of the driver. The mouth over eye aspect ratio was set to 2.6 and above to indicate fatigue status. So the robustness of this system, we had got an accurate fatigue detection across the various driver scenarios, and the real-time feasibility, we had achieved a lightweight architecture suitable for real-time applications. So in the discussion part, the strengths of this research, the robustness, we had a very accurate fatigue detection for the real world in different light condition and different road maps. Scalability, designed and integrated with like we can add the sensors that we want to add to this research, and we can across it to a diverse driving populations. Real-time application, it's a lightweight architect, so we can enable it on the fly to detect for detection and intervention. So the limitation of this study, a single driver that have been hired for this. In the future, we're gonna expand that and extend that. And it was the VDM, sorry, which is the vehicle dynamic measurement, was have been excluded from the parameters where it's that being fed to the CNN and LSTM in order to detect fatigue, non-fatigue. So in the future, that will be fully integrated. So the future work, we are looking for a larger data set, including drivers from various age and sex for cognitive profile under different environment conditions, weather, time of day, and scalability designed to be integrated to additional sensors across the diverse drivers population, and the VDM will be included in the future research. So the summary of this presentation, the multimodal fusion combines behavior, physiological, and vehicle dynamics, and that dynamics data for improved accuracy and reliability. CNN LSTM for temporal analysis effectively identifies fatigue status by analyzing sequential data, scalability, adaptable for real-time use in advanced driver assistance system ADAS. So I would like to acknowledge the Innovation Center at Transport Canada that was part of this research. They had contributed a lot, and we are looking forward to do great research in the future. And also the resilient ground transportation known by RGT program at the National Research Council Canada. That's all for my presentation. That is my LinkedIn QR code. If you would like to reach me out, please scan it and reach me out, and I will be more than happy to answer all your questions. This is my email address, abdullah.georges@nrc.nrc.gc.ca. Please feel free to shoot me an email if you would like to, if you have any questions or you're looking for a further chat. Thank you very much for attending my session, and see you soon.